Okay, I'm very happy to introduce today two speakers. The first speaker is Igor Malheiros. He very recently received his PhD in computer science from University of Montpellier under supervision of Michael Poss and Anand Subramanian. And he worked on robust optimization for routing problems and conducted this in also work in collaboration with Atop Tima in Bordeaux. So he developed scalable optimization algorithms for supply chain planning. I'm very happy to have you here, Igor. So please.
Thank you very, very much, Yanis, for the introduction, and thank you for the invitation. It's a pleasure being a robust optimization webinar. So the title of my talk today is Iterated Local Search Algorithms for Adjustable Robust Optimization Problems with Discrete Budget Uncertainty. And this is a joint work with Oscar Flores, Henri Lefebvre, and Michael Pos. So the problem definition, so the problem that we are addressing here in this talk is adjustable robust optimization problem with discrete first and second stage and budget uncertainty set. So we have some first stage decisions X and some cost associated already with these first decisions. We have the adversarial problem that tries to find the worst case scenario. And we have our recourse decision that depends on the decisions of the first stage and the scenario. And we have also some costs associated to this recourse decision. And we assume that the combinatorials, that X is a combinatorial set, that our uncertainty is modeled as a budget uncertainty set, and Y is also a combinatorial set. We will also assume that for any fixed X and n fixed Psi, our recourse problem can be solved exactly and efficiently for instances of practical size. So it means that, for example, this recourse problem may exist some polynomial time algorithm that can solve, or some specialized algorithm that can solve it pretty well, or we can address this by commercial MIP solver and so forth and so on. But even if this problem is easy to solve, it's still the inner max-min problem remains computationally challenged to be addressed. So our proposal to solve this problem is the following. So we're gonna solve the recourse problem exactly. So for a fixed X and Psi, we're gonna solve the recourse problem exactly. So we name here as G of X and Psi, and we optimize over Xi. And then we can optimize over Xi in two ways, either exactly. So we're gonna define H of X, that is this, the optimization over Xi exactly, or via local search that give us underestimation of the worst case scenario. And it's named by the tilde H of X. And we're gonna optimize X via iterated local search. So since we have two ways of optimize over Xi, this gives us two ways of optimize over X. So if we use the exactly estimation of H of X, it's gonna be an approximation tilde Z. But if you use the underestimation H of X, we're gonna have double tilde Z. So it's important to notice that the value of double tilde Z cannot be compared to the true optimal value of the original problem because we are using an underestimation of the worst case scenario. So this means that for a given candidate solution tilde X, it's necessary to compute H of tilde X at least once to properly evaluate the robustness of the solution. However, computing H of X tilde for a fixed X tilde, it's still easier than optimize H of X for all possibilities of X. So the framework here is the iterated local search. So here is a flow chart of a standard algorithm of the mood start iterated local search. So the idea here is basically you have two nested loops. So you start with some feasible solution, you perform some local search trying to improve your solution. If the stop criteria is achieved, is not achieved, sorry, you perform some perturbation trying to escape this local optima, and you perform local search again. And you keep doing this loop until some stop criteria that can be either a limited number of iterations or some time limit. You keep doing this loop, and you also have the outermost loop that there is another stop criteria that if it's not achieved, you just restart from another feasible solution and do it the inner loop again. So of course the algorithm it will stop once you achieve the both stop criteria. And the main challenge here is because for every of these components, you have to evaluate your incumbent solution a huge number of times. And to evaluate this solution, it means that you have to solve the maximum problem that is already very time demanding to be solved. So the idea is introduce some key ideas in such a way. Either we can do this in a more efficient way, or even avoid to evaluate the solution, exploiting some properties of the problem and some other structures that already exist in the literature. So our first idea here is evaluation speed up. So for a given feasible solution X, such that the objective value is given by the first stage solution plus h of X, if we have any neighborhood solution X prime, such that X prime is a neighborhood solution of X, if the first stage cost of X prime is already greater than the total cost of X, then X prime cannot be an improvement solution, and we can just skip the evaluation without having to solve h of X prime. So this is avoid to solve the maximum problem for the X prime, and we can just skip the whole evaluation and make the whole exploration of the neighborhood faster. Another idea that comes from the literature is implement the mechanism of the memoization move descriptor. That for each of the neighborhoods in the local search, we have a dictionary. And so the key of the elements of the dictionary, this dictionary, are the hash function applied for a solution. And the value associated to that key is the modifications necessary that you have to do in this solution X in such a way you're going to obtain the best improvement solution associated to that neighborhood. Or if it's the case that the solution is already in a local optima, it's just a flag saying that there's no improvement solution. And once you have this dictionary, every single time that you have to explore a new neighborhood for a given solution, you're going to first check in your dictionary if these elements already exist. And if it exists, you just retrieve the modifications necessary to obtain the best improvement. Or if it's already a local optima, you just skip the whole exploration. And in both ways, you're skipping the whole exploration, and you don't have to re-explore all the neighborhoods and evaluate all of them, which leads to solve all the maximum problems again. If it's the case that this solution, it does not exist in our dictionary, so we're going to perform as usual. So we're going to explore the whole neighborhood again in trying to find the best improvement solution. And once you find this modification necessary to find this best improvement solution, you're going to store this in our dictionary. So this is one strategy that can avoid a lot of recomputation of a neighborhood once you have already treated that in your search. So I'm going to show you now some applications that we model in our framework. So the first application is the multiple knapsack problem. So how it deals the multiple knapsack problem. So you have first stage decision that you have to assign different items to different knapsacks. So this is the first decisions. You just have to do some assignments. Then you have the uncertainty realization that the real weight of the items, it will be revealed. So once these weights are revealed, you have to pack them of course, respecting the capacity limits of each knapsack and trying to maximize your profits. So these are the mathematical description of each decision set. So we have X here, that is a binary vector for each item in each knapsack, and you want to assign exactly one item to each item to exactly one knapsack. We have our budget uncertainty set that have to sum up to gamma, and we have our recourse set here for a fixed X and Xi. We have a Y binary matrix that says that you have to, for each knapsack, the capacity limits of the knapsack must be respected. And the deviation is taken if the scenario is activated or not. And Y, it's only activated if it's already assigned for the knapsack K. And the formulation, it's over those sets, it's given by that. We want to maximize the profits over the worst case scenarios. So the implementation details for this, for our framework, for this problem, for this application. So we have to represent each decision as a data structure. So the first stage decision, it's represented as a partition of items into knapsacks. We have a vector psi hat to indicate whether each item faces the worst case deviation or not. And we have a hat Y, which is a binary matrix that says that if item I is packed in the knapsack K. So we also have to define some neighborhoods for the first stage decisions, but also for the adversarial problem. So for the first stage decisions, we can, for example, reallocate one item that is assigned to a knapsack to another knapsack, or we can swap items that are assigned to different knapsacks. For the adversarial problem, so we can swap one active and one inactive uncertain component. And we have also a neighborhood that enumerate all possible, all combinations that sums up to gamma of deviations taken. And this is, of course, it's a exactly way to solve the adversarial problem because we are enumerating all the possibilities. So for each component of the algorithm, so the constructive procedure, it's a very basic heuristic. It basically randomly assign each item I to a knapsack K. Our local search selects the order to apply the neighborhoods in a random way. And the perturbation randomly choose one of the neighborhoods to be applied and a random move of that neighborhood to be applied just to escape the local optima. You do this a limited number of times trying to escape. And for our evaluation, the adversarial problem, we have two implementations. So we have one that do the enumeration and solve the adversarial problem exactly. And we have another one that performs a local search on this on the adversarial on the vector hat Xi. And once we have fixed the Xi and the X, we have to solve the recourse problem. So the recourse problem here relies on K independent knapsack problems. And we can address this using specialized knapsack algorithms, for example, the ones by Pissinger. Our second application is a facility location problem. So in this problem, the first stage decisions are which facilities should be open. And then the realization happens. So the realization here, it tries to disrupt one of the open facilities. And among those open facilities that were not disrupted, we assign customers to those facilities, respecting the demand and capacities, the demands of the customers, the capacity of the facilities, and minimizing the assignment costs. So these are our decision sets. So X here is the binary vector that indicates if a facility is open or not. We have the same budget uncertainty set for each facility. And we have our record set here for a fixed X and Xi. It says that each customer should be assigned to exactly one facility, and it must respect the capacities of the facilities for each each of the all the customers assigned for each facility should be respect the capacity of the facility if it's the facility open and it's not disrupted. And then we have the formulation through these sets, so we can minimize the open costs and the assignment costs. So the solution representation of these sets in our model are very simple. So we have a binary vector to indicate whether a facility is open or not. We have a binary vector to indicate if the facility is disrupted or not. And we have a binary matrix Y that just say if a customer J is assigned to a facility I. So these are the neighborhoods of for this application. So we have the first neighborhood that open for a given facility. If the facility is closed, it will open. If the facility is already open, it will close. We have the neighborhood that swaps one facility open to another one closed. So one that's closed, it's going to be open, and the one that is open is going to be closed. So we perform this at once. And we have only the enumeration here of uncertainty vector. So the adversarial problem here, it's always solved exactly via enumeration. So our constructive procedure, it selects gamma plus 2 facilities to be open using a ruled selection based on the ratio of the capacity of the facility divided by the the opening cost of this facility. The local search, again, it randomly selects the order that should be applied, the neighborhood should be explored. And the perturbation, again, it will choose randomly one of the neighborhoods. And once you choose this neighborhood, it will apply a random move in your current solution. So for the evaluation of this problem, the adversarial problem only solved this exactly, but to make this enumeration more efficiently, we search for the scenario only among the scenarios that solutions that are open. So it means that our enumeration, it depends on the first stage decisions. And so with that, we only have to enumerate among the facilities that are already open. And the recourse problem relies on solving generalized assignment problem. And we address this generalized assignment problem via Gurobi. We just have a MIP model and solve it. So now I'm gonna show you some computational experiments of these both applications. So we implemented this multi-start iterated local search for adjustable robust optimization as a library in C++. And also in all the applications use that library. And in a near future, we want to do this all open source. So the library itself and all the applications. And we benchmark this with instances of the literature for the multiple knapsack problem and for the facility location problem. And we compared with some exact algorithms. So the first one for the multiple knapsack problem, we compared with the branching cut from Lefebvre et al. 2024. And the facility location, we compared with the column and row generation with mixed integer bi-level solver from the framework of Lefebvre. So these are the first results for the multiple knapsack problem. So we'll first take some attention for the branching cut here for the exact method. So we can see as the gamma increase, we can see that the percentage of solutions that are solved to optimal decrease. So when gamma is equal to 1, the exact algorithm could solve around 90% of the instances, but when gamma is equal to 4, it's decreased to around 50%. We have the times, the computational time on average necessary to solve those instances. So this is among the instances that were solved to optimal. And among the instances that were not solved to optimal, we have these gaps. So jumping here for this third part of the table, where we have our framework that solves the adversarial problem by enumeration, we can see that in all runs, we could achieve the optimal solutions. And among the instances that the exact algorithm could prove optimality, we also decrease a bit the gap. So here we have a small decrease, here we have a small decrease, and here we have a better decrease for when gamma is equal to 4. And then we have the time on average necessary to solve each group of instances. So it never goes on average more than 64 seconds. In the middle part of the table, we have our framework that address the adversarial problem via local search. So in that case, unfortunately, we could not find all the optimal solutions as among those instances that the exact algorithm could find the optimal solution. And also the gaps are a bit worse than the exact algorithm. However, the time necessary to compute this is very short. So it never takes more than 5 seconds in average to finish our algorithm, and it can already obtain some more or less good solution. For the facility location problem, we have the column and row generation plus mixed integer bilevel solver. So here in those instances, again, this column represents the percentage of instances that could be solved to optimality. So as the gamma increase, this percentage decrease. This is the time necessary to solve those instances to optimality. Here is the percentage of instances that could not even be possible to find a primal solution, a feasible solution. And these are the percentage of instances that it could be possible to find a feasible solution, but it was not necessarily optimal. It was not, that's no optimality proof. And these are the gaps associated to these instances. Here we only have our setting with the adversarial problem solved by enumeration. Among the instances that could be solved to optimality, we again could obtain very good results in most of the time finding the optimal solutions. We always have some primal solutions, so we can compute the gaps among those instances that the exact algorithm could not find any feasible solution. And the gap among the instances that could be find a feasible solution, but not necessarily optimal, we could also decrease the values. And the time necessary to compute among all of those instances, it remains a bit short, so not on average, never more than 70 seconds. So as a conclusion, the main contributions of this work, it's proposed a start iterated local search framework for adjustable robust optimization with discrete first and second stage. So we are proposing also some speedups for evaluating the three-stage structure. And we integrating some speedup mechanism from the literature for this problem. And we finally perform some computational experiments on benchmark instances. And as a future work, we want to study some applications and apply our framework for some fortification games. And we want to also evaluate the impact of each speedup mechanism. And that's all. Thank you very much for your attention.